Welcome to Data Science 1, Probability, the uniform distribution. Okay, some things that we need to remember. Sample space, random variables, cumulative distribution functions, probability density functions, as well as some expectation. Now, the first distribution we're going to look at is probably the one you'll perceive to be the least useful, but it's the easiest one to start with. But as we go through it, you'll see that it becomes quite useful later. So suppose we know we have an experiment that we are interested in that has a random variable that is equally likely to put any value anywhere between 0 and 1. Since each value between 0 and 1 is equally likely, then our density will be equal. Okay, it'll be some constant on the interval 0, 1. And it's easy to figure out what this constant is because we know the density must integrate to 1. Since it must integrate to 1, well, remember, this thing is a picture of it here, right here. It's a rectangle. We already know that it goes between 0 and 1, so we have the width. Now all we need is the height in order for it to be 1. Well, if we know the width is 1 and we know the area is 1, then the height must be 1. And we did all of that without calculus, but later we'll have to use calculus to come up with some of these. Okay, so let's use this for something. Suppose we know that x is distributed uniform 0, 1, and we want to know the probability that where x falls between 0.2 and 0.6. So we could use calculus, but this is a rectangle. Area is height times the width, and here the height is 1, so that makes it really easy to calculate this. It's just the subtraction of the two, right? It's 0.4. Super easy to calculate in this case because we really don't need to use any calculus. Here's the CDF. Easily found by using basic calculus. I'm going to skip the steps here. But if you notice, it's 0 from negative infinity to 0. It is x from 0 to 1. And it's 1 from 1 to infinity. So it looks like this. Okay, so it's going to have a 0 down here and a 1 tail up there. So keep that in mind as you're going along and working through these things, that whenever you're dealing with a CDF, it really needs to be defined on the whole real line. Okay, so suppose x is uniform 0, 1, then the mean is given by this. So we can work through it. Mu equals the expected value of x, integral from negative infinity to infinity of x f of x dx. This was from the last video. Plug in f of x is equal to 1, so we integrate this thing and we end up with a half. But this looks like an awful lot of work when we could have just looked at the picture, right? It's the balancing point, and if it's uniform, it should balance at a half. Okay, I'm going to skip the steps on the variance, but if x follows a uniform 0, 1, then the variance of x is given by this, which is the variance formula for continuous distribution from our last video. Here's the formula once we plug in mu of a half, and if you do all the algebra and calculus along the way, you'll end up with 1/12. And I couldn't have guessed that from the picture. But anyway, this is the number you'll end up with. So we're going to quick summary of what we know about this distribution right now. So that we know the PDF is 1 and 0. If x is between 0 and 1, it's 1, or 0 otherwise. Here we have the CDF. The CDF goes from 0 from negative infinity to 0, and it's x from 0 to 1, and it's 1 from 1 to infinity. We know the mean is a half, and the variance is 1/12. Now, later, this distribution becomes extremely useful, especially when you want to do random number generation. Okay, but we'll leave that for later, but I'm just letting you know, while it seems like this is not useful because you can't think of an experiment that would give you this type of answer, don't think that it's not useful for other things. All right, so we're going to move on to a list of distributions here in the future, so stay tuned and see you there.